Hello everyone, and thank you for being here for this presentation, which will discuss the EEFIT work, the EEFIT mission after the September 2023 Morocco earthquake. So as most of you, probably all of you know, on the 8th of September 2023, there was an earthquake of moment magnitude 6.8 in the High Atlas region in Morocco, and this earthquake caused extensive damage to structures, infrastructures, but together with this damage, the event also triggered numerous landslides, which obstructed some of the transportation network and isolated some remote areas in the High Atlas Mountains. So as a consequence of this event, there were substantial losses with approximately 3,000 casualties and more than 6 million people affected. So although this was an extremely dramatic scenario, this also offered a unique opportunity to learn more about these events and the consequences of these events. And so through EEFIT, we organized a mission to learn more and possibly to prevent similar disasters in the future. So this evening presentation will focus on the key results of the EEFIT mission and will provide an overview of the mission findings, including considerations of the distribution and activation mechanism of the co-seismic landslides and the extent of earthquake damage to buildings and more in general to infrastructures. So let me introduce the presenters of this evening seminar, which are the Associate Professor Viviana Novelli, which is Associate Professor in Civil Engineering at Cardiff University. Her research focuses on advancing multi-risk decision support tools to reduce the impact of natural hazards in terms of minimizing the consequences in terms of human losses and socio-economical losses, and her work focuses especially on developing countries. So Viviana was very much, her research was very much aligned to the mission, and her expertise was very useful during the mission. The other speaker, I thought I had to introduce him, but he already introduced himself in the previous presentation. So he's Michael Whitworth, which is the Vice Chair of EEFIT. So Michael is a Technical Director in Engineering, Geology and Geomorphology with 20 years of experience working in several countries worldwide. He has extensive expertise particularly in geological and geomorphological mapping in a range of geological and climate setting, including tropical climates, and he was part of several EEFIT missions, including the mission to Nepal in 2015 and 2022, the mission to Haiti in 2021, and of course the mission to Morocco, focusing in these missions, his focus was on the impact of earthquake-induced landslides to structures and infrastructures and to the transportation networks. So, without further ado, I leave the floor to the speakers.
Right, good evening to everyone. So thank you, Fabio, for the introductions. This is the talk outline. So very briefly, I'm going to introduce the earthquakes, and then I'll move and how we have set the teams for this mission. And then I will pass to Mike, who will discuss more about the geological settings and will focus particularly on the seismotectonics of the 2023 events. And then he will move to discuss about the earthquake impact and landslide that were triggered by this seismic event, giving first an overview, and then he will also discuss about how the remote sensing has been used in order to identify the landslides, and then how this has been combined with work that has been done on the field. Then Mike still will also discuss about the geotechnical observations, and will link actually how the geotechnical issues has triggered some building damage, and how these are connected to the geology. And this will introduce the second part of the talk, where I'm going to discuss about more in details the structural assessment that we have done. First, identify which are the most affected regions in Morocco by this event. And then I'll discuss about how we have carried out the field damage assessment and how the data collected on site has been then combined again with the remote sensing. And then I'll move to more detailed assessment, and we will see together which are actually the failure modes and the mechanisms that we have observed on the residential buildings as well as non-residential buildings. And then we are going to look also which are the monumental cultural heritage that's been affected by the earthquakes, and we're going to see which are the ones that we have inspected on site. And then I will very briefly talk about the recovery and resilience effort and providing some conclusions, and then I'll leave the floor to the audience for some questions. Right, this was the 8th of September of 2023, that at 23:11 local time in Morocco, there was an earthquake with a magnitude of 6.8, and after that there was another aftershock of 4.9 after 90 minutes. So this was the news that we were looking after the earthquakes occurred. And as you can see, there was so many different news and also many vivid pictures showing which was the level of damage, or mainly concentrated on villages that are very much isolated and built on mountains. In the news, we could read as well that there were so many villages that they were completely isolated, and that they were really in need of suppliers, essential suppliers. And the reason why was because many roads were completely blocked by landslides. And at the same time, we were reading that people were in need, and also there were also many news about many heritage sites that they were affected, and as well as some historical mountains. As usually happen when this type of events occur, the new coverage highlight the human impact, but there was a very limited details about the technical aspect of what happened on the field. So the EEFIT, as soon as this earthquake occurred, decided to launch this 80-man project that, as has been mentioned by Mike, we actually at that time we were running out of funds. So we applied for UKRI funds under the NERC urgency grant, and then we got a grant for 18 months to assess, actually to try to understand much better the earthquake process in arid mountains environment, combining multidisciplinary expertise across structural engineer, geotechnical engineer, geology, geomorphologists, and remote sensing. The idea was to use this time to try to understand the key factors driving landslides, and also the geotechnical buildings failures at urban scale and also at more detailed scales. Why all of this was aimed at try to understand the impact of how we could reduce, of course, future earthquakes, the impact of future earthquakes in Morocco, but also in other geographical settings that are very similar to Morocco in terms of geomorphological point of view, and also buildings. Why this matters particularly? Because earthquake in interplane mountains areas, and this will be discussed very much by Mike, are very rare and make this very particularly unique. So these missions was led by Fabio, Mike, and myself. And as soon as there was these earthquakes, we asked EEFIT members to express their interest on participating to these field missions. And based on their expertise and interest to the mission, we created different teams. So as you can see, we had a landslide team, a structural team, and also a remote sensing team. So all the expertise were fundamental considering the type of events that occurred. Also, we had a support from remote, and then when we started, started the project, then we found out also like the way to collaborate with local partners. We had local partners from university and NGO that have been fundamental on from the logistic point of view, also to understand exactly what was happening on the ground. Say that, I'll pass this to Mike, the floor, so you can talk about your...
Thank you very much, and thank you, Fabio. So what I'm going to be taking you through is really the geological, and then taking you through sort of the earthquake-induced landslides, which was one of the core reasons that we were looking to investigate the Morocco earthquake, and then also looking at some of the geological and geotechnical observations that we observed. So for those of you that aren't aware, Morocco and the Atlas Mountains are located basically within the African plate, which is actually quite complex and has various interactions with the Eurasian plate, which basically causes a range of different types of rifting. The interesting part is in northern Morocco, the African plate is approaching the Eurasian plate at approximately 4 to 5 millimeters per year. And that's the main control of seismicity within the Atlas Mountains, which is controlled by this deformation associated with this collision, which is why this sort of event is quite rare of this sort of magnitude. So historically, within Morocco, they have about 25,000 earthquakes in the region since 1901. But only about 9 greater than magnitude 5. The most notable events were in 1960 in Agadir, a magnitude 5.9, which killed 12,000 people. And then in 2004, a magnitude 6.3 killed 629. So large events in Morocco are quite rare. So the main shock occurred. I've been told that I've got to use a separate thing for a pointer, but I believe people on screen. So the main shock occurred here on September the 23rd, a magnitude 6.8 with approximately 3,000 fatalities, and it was the most deadly since the 1960 Agadir. Unfortunately, approximately 2,000 people from one town were killed, so a large number came from one village or one area. The damage estimation was estimated at 7 billion, and it occurred within an area of low historical seismicity, and it did not rupture the surface. So the causative fault is not immediately apparent. So the initial thoughts and the initial theories was that basically there were 2 possible mechanisms. On the left-hand side, a high angle north-northwest dipping fault, or a low angle south-southwest dipping fault, and the aftershocks, so basically that was the idea, but the aftershocks basically after the event seemed to indicate that it was more aligned with the low angle fault. So the event was recorded on the Mercalli scale as being severe, with moderate to heavy damage within the area. And peak ground acceleration ranged from about, I can't see the numbers, sorry, because of the screen, from around 20, oh sorry, I've got the number, from around 50 up to with peak ground velocities in the region of 20. So that gives you a little bit of the sort of geological and seismotectonics. But then looking at the earthquake-induced landslides, one of the reasons we were so interested is in the news, and we can talk about this a little bit later, but it was very quickly reported the impact of landslides on the recovery and rescue. And this is a BBC photo taken at the event that was reported very, very early, indicating about the hampering of earthquake-induced landslides and the impact this was having on the recovery and rescue. So this basically focused our minds around the NERC grant and the EEFIT mission, looking at earthquake-induced landslides and the impact that they might have. One of the reasons we look at and are interested in these landslides is they not only have immediate impact following the event of hindering the immediate rescue and recovery, but they also have long-term impact in the landscape where they cause long-term and often decades long-term impact, potentially leading to future landslides and future impacts in the area. And this idea is sort of illustrated in here, where you get a range of initial hazards, but then a range of different cascading hazards and failure over time. So it's a really interesting case study of looking at initially why were these landslides occurring and the impact that they had. So just again to just talk about the geological setting. So again, it's an intraplate tectonic setting where large earthquakes are rare. Its climate is arid, and its topography, the typical relief of the area that we investigated, was 2 to 4 kilometres. For the non-specialist, the bedrock geology was quite broad. It's sort of shown here on the geological map, of being a range of Cambrian schists, Jurassic limestones and Triassic sandstones. The soils typically, and we'll come on to the soils a little bit later in some of the geotechnical observations, were typically coarse quaternary alluvial gravels. So our initial approach, as Viviana talked about, as we were setting up the mission, we had a 1 to 2 month window before we launched the mission in person, and we looked at using a range of different remote sensing techniques. A lot of lessons that we'd learned from the Haiti mission, because we did that remotely. That gave us the opportunity to utilise and learn and look at and investigate a range of different techniques that could be applied to basically post-earthquake, post-disaster scenarios. So the team from Delft, led by Georgia, initially looked at using synthetic aperture radar, and then we were also supplementing that with optical imagery. And the reason for this is obviously we can cover a huge amount of areas very quickly, and also start to look at and pick out some of the major features. It also allows for effective planning of the mission. Obviously, the mission is only a week, 10 days, and it allows to focus the effort on the areas of most interest. So we'd actually had, and quite a lot of success, looking at using SAR to identify landslides, looking at and using the intensity map when we did it from Haiti. So there was quite a lot of success with that. But what we found, and we can discuss this later, but using the Sentinel imagery, which was 10 metres, was found to be insufficient in this case. The problem is that in Haiti, the landslides, you had highly vegetated areas, and where the landslides occurred, you had devegetated areas. So the contrast between the two and the intensity on the SAR amplitude was quite high, so they stood out. But in this arid climate, also the size of the landslides that we eventually, which we'll go on to, were much smaller, but also the intensity and the reflectance between the landslide and the arid environment was not strong enough to enable us to really effectively pick these out at this 10-metre resolution. So if it's 10-metre resolution, typically you're probably going to be looking at a landslide greater than 100 metres squared. So it's got to be a reasonably sized landslide. You can't pick out a 10-metre landslide. You've got to have several pixels. And you'll see from some of the photos and some of the images that a lot of the landslides were quite smaller. Unfortunately, the higher resolution INSAR data was only available post-event. So that's in sort of centimetre to metre scale. So we didn't have pre and post imagery to be able to identify the landslides. So that took us back really to the times pre-INSAR, where we were looking at optical imagery. And we were quite fortunate that Maxar released quite high resolution, 30 to 15 centimetre data, pre and post imagery. And in the centre there, pretty much the area where we had good pre and post imagery is shown in the green. And then basically in the orange was where we basically had no post imagery, only pre. But you can see we had quite good coverage adjacent to the epicenter. So this is an example here of the Maxar data pre and post imagery. So you can see the before and then the red dots picking out some of the images, some of the landslides after. As you can see, there's quite a lot of distortion within the imagery. So this is basically geodetic, so it's not really been topographically corrected. And this actually caused a lot of problems of actually being confident in a lot of the landslides that we identified. And obviously there were a lot of data gaps that also hindered. But we were able to identify quite confidently 464 landslides. Since the field mission, we are actually going back and remapping with that renewed confidence of what we're actually seeing in the aerial imagery of what is a landslide and what isn't. And it's likely that this number will increase slightly. But for those of you who attended any reports on the Nepal mission, 465 compared to Nepal, where they had over 26,000 landslides. So compared to what the news said, to what we actually saw, you know, the perception that was given that there were huge amounts of landslides was not actually the case. So why was that? And that's really one of the research questions that we're still investigating. So just a little bit of a summary. Most of the landslides occurred in this catchment. There's no obvious geological control initially. They all pretty much occurred in most geological units. The landslides that we identified from the aerial imagery were predominantly small block flows, and there's lots of potential reactivation. So that was really the remote sensing aspect. So what we then went to do, and this is just a very quick summary, looking at the field validation for the landslides. So basically we used one of the main roads, the R203, I think it is off the top of my head, looking at basically mapping along that road route, which is where a lot of the landslides occurred within close proximity. So you can see in the upper left, you've got basically a small sort of granular flow within the Cambrian schist. To the upper right, you've basically got a block topple and fall, turning into a sort of a granular flow or debris flow within the Triassic sandstone, and similar sort of morphology within the Jurassic limestone. And then again, you've got some smaller failures occurring within the Quaternary coarse gravel. And what you can see is a lot of these are initiating at sharp breaks in slope or changes in slope, which is quite classic for earthquake-induced landslides. There's quite a lot of work has been done which identifies sort of topographic amplification and topographic effects that has quite a significant control on landsliding. Now we do have a little bit of a problem, so this is also a little bit of a thing. There has been quite significant reactivation of existing landslide material, so obviously that's a causative factor, looking at where existing landslides were. But some of them, both in the field and within the aerial imagery, was quite difficult to identify whether reactivation had occurred. So on the left-hand side is a clear example. You have the pre and post imagery with the field observations, and then sort of the unclear example where you've got the pre and post imagery down the bottom, and then you've basically got the landslide material, and you can see that it's very difficult to pick up sort of fresh scars or fresh material within that morphology. So it was quite challenging to actually identify which landslides were earthquake-induced and which were pre-existing. Now, we identified predominantly that the landslides and the earthquake-induced landslides had significant impacts on the road infrastructure. On the upper left, on the left are sort of the major roads which lead into the area and lead into the mountainous area, and these landslides from basically from local knowledge, they told us that impacted recovery by closing the roads for 2 to 3 days after the event. But it's also worth bearing in mind that this is a very rural community, and rural tracks are also quite significant, as that's the way that they travel to get into the remote areas where their villages are. And we're talking, you know, motorbikes and on foot. So a lot of rural tracks were also impacted and still going on as sort of still impacted over time. We did identify some minor impact to sort of telecommunications, but by the time we visited in the mission, that had already been repaired, so quite quickly after the event. So just to give you a little bit of a drive through, this is a short little video and sort of gives you an idea of the impact. This is actually a major road. It's now being, interestingly, it's now being turned into a motorway, a 4-lane, they're actually building a 4-lane motorway, and Viviana has got some photos of that a little bit later. Now, the interesting thing, and this is something we're trying to pick up and look at a little bit more, is this is on the background of this slide is the landslide predictions from the USGS and the pager information, which has been known to be quite accurate. But what we identified is that the observed landslides didn't really match the predicted. Now, that's partly possibly linked to the fact that we didn't have all of the aerial imagery available, but it's also possibly a factor that uses basically slope angle and seismic parameters, where in this case, because it's an arid environment, it's a different environment, it's probably linked more closely to the geology and geomorphology as a control, rather than purely the topography. So this is something that basically we probably need to investigate and look at further into the future. So just very quickly, some of the geotechnical observations beyond really just purely the landslides. Now, interestingly, there were not as many as we'd anticipated. That wasn't a fact of the earthquake, it was just the fact that not a lot of geotechnical structures really existed. So this is just some slides. So obviously I've talked about the landslides and the earthquake-induced landslides, but what we identified actually is that the road building that is ongoing, that was actually paused during the earthquake and for the 12 months after, but has restarted, actually probably preconditioned the slopes to the earthquake-induced landslides. So you can see here on the slides that they've oversteepened quite significantly the slopes, although partly benched, and also highly fractured the rock, and pretty much there's no evidence of any form of stabilisation. So we think part of the causative factors of so many landslides along the road network was part of the preconditioning caused basically by human interference and anthropogenic interference. We identified also a range of tension cracks within sort of retaining walls and minor impacts to structures. The fact that we only saw a few is the fact that only a few really existed. And in this case, it was really probably due to the way that it had been built out. You can see here that this is built on a bend. So what they've probably done is they've excavated into the cliff and then side tipped and then built the road on partly on the side tip and partly on the rock. And what has probably happened here, although we couldn't really get down slope because it was quite steep, is that probably the tension crack, and that is interfering along that, almost along that interface between the basically the fill and the rock, and basically the change in basically amplification and signal has caused some of those failures. You can also see in this picture there's quite a lot of rock falls that have caused a range of different damage, sort of quite minor damage to basically some of the retaining structures. We were also asked to go and visit a small school to look at the impact of basically sort of retaining wall failure, but this is basically really just basically some minor spoil that had failed. But what was actually more of concern, I don't know if it's in the next slide, is actually the retaining structure just below the school, where the retaining wall had basically, there was a retaining wall here which had performed well, but below the school there was actually no retaining structure there, and that geology was starting to fail. Whether that was earthquake induced or whether that was just over time that had occurred, but that was an area where they had issues. So just finally, and maybe as a little bit of an introduction into looking at the building damage and linking the two, we started to identify, obviously we initially went out there looking at landslides, but as we're sort of moving around the landscape, working with Martin and others, it started to identify that geology was playing quite a critical control on building damage. And this is an area that we're looking to investigate a little bit further, but it looks like a lot of the building damage and a lot of the significant damage was on these superficial deposits. The locals build on these areas for a variety of sort of anthropogenic reasons, both cultural, economic, building on these often flat-lying areas where it's easy to excavate and build their foundations and build their buildings. And we started to identify, and further work is being done to investigate this link between geology and really building damage. But it was starting to become quite obvious that a controlling factor was the quantity of, or the quality of buildings on these soft superficial deposits. But as I mentioned, further work is required. So without further ado, I'll hand you to the star of the show. Thank you very much.
Right. So now we're going to talk about what we have done looking to buildings. So this is quite what we were observing when we were driving all around in Morocco. And so has been mentioned about, Mike was just mentioning about these villages that very often they are built like on these mountains. And then they are quite isolated when these roads are completely blocked by landslides. And also, the point is that these villages, they're very often self-built. So, people in the villages, they build their own houses. So this means also that they use like some substandard materials. And very often there is a very little input from engineering. The point is that when you go through these villages, it's very, very complex to understand what is happening around, for the simple reason that you walk through these villages and you can see that there are so many different buildings that are also very difficult to associate to worldwide classifications of buildings. So because we are going to discuss this a little bit more in details where I'm going through and explaining the damage and the failures. But this is just to give you a picture of what we were seeing when we were around. The first things that we need to do when we are planning our missions, so is try to understand which are the areas that are highly affected by the earthquakes. And this is actually a very complex, we were doing this through local partnership, looking at the census and also with the support to remote sensing. So the first things we were like, with the help of our local partners, there are, here you can see some of, with the symbols that are some of the partners that we have locally. We were talking about what was happening on the ground and also having contact with the local authorities. So, and then trying to make sure that all the activities that we were planning were actually trying not to interfere with what was happening on the ground. And of course, making sure also that all our activities was in health and safety. Then what you see here on the, what is this one here? Okay, yes, what you see here, right? Maybe, right, this one, okay. So these are the 6 regions that have been most affected by the earthquakes. And on the plot that you see on the top is actually the percentage of communes that has been affected, the one not affected in a single region. And then on the bottom you see also the population by province, and we have a comparison here between population 2014, so by the census, and the actual population. You can see that over the last 10 years there has been not a significant change in terms of populations. But at the same time, also, again, going back to this region that I was showing here, right, all the regions, there is a high percentage of rural housing on all these regions. And when we talk about rural housing, they are very often informal development and without a very construction practice. What you see here is like not following really the seismic code, that the first seismic code in Morocco was in 1960 after the Agadir earthquakes, there was a major one. And then these are some guidelines that also for traditional construction, but not really follow. So what we have done as a second step is look at the census and try to understand which is the building age, the floor materials, the wall materials, and roof materials. This is from one of the regions that was considered one of the most affected one. And these are very informative because then we have compared what we have seen from the census for the observation on the site, and we will come back to this slide later. And then remote sensing, fundamental, and I try to understand the regions that are most affected. During this phase, the remote sensing team was acquiring different spotlight data that then has been used later on for extracting a building footprint and to calibrate tools that they have to predict the damage. Once we have identified the regions, then we prepare our own form for the data collection. I know there are so many different data collection apps and tools that are available, but as you have seen from the beginning, it's very complex. It was really complex for us to use one available tools for the simple reason that the topologies are very complex, and then we want to make sure that we were very effective when we were on the site. So these are the information that we were collecting, and these are the buildings that we had collecting when we were in the field. 445 buildings with a very simple form that takes about 15 minutes to fill, and we were taking a lot of geo-tagged photos. So what you see here is the main typologies that we have identified. Confined masonry, the major one, something that we call mix, and we will see later on what that means. Then we have some traditional construction, rammed and stone, very small percentage of reinforced concrete buildings, and then some of them was difficult to identify. So, and then we have classified all these buildings through the AMS 98, and here you can see the distribution, but we'll come back to this damage distribution later on when we're going to talk about the single typologies. One thing that I want just to highlight here is that when we were in the field, these are the major building typologies that we have identified, and this is the data from the census. By comparing those, we see that the highest percentage for the field is confined masonry, while for the census 2014, the major is, the reclaim, oh, that's not the wrong, I just put the wrong one, but actually there was just a mismatch completely. This is for the floor, sorry for that, I just realized that. But there was a complete mismatch between what was reported in the census and what was reported in the field. So we have used remote sensing to do also, of course, some maps where we have mapped all the data in terms of damage and the typologies. And then at the moment, remote sensing team is actually using our field data in order to calibrate the tools and try to predict the damage based on the 5 classes, but mainly concentrated on the intermediate classes. So in a way that so DG2 and 3 that are most difficult to identify by remote sensing. Right, now what we're going to do is to talk about the structural assessment that we did in details so we are going to discuss exactly which are the failures that we observe on the site. So these are, as I said, confined masonry, the major one, but we start from the traditional. So again, as Mike has mentioned, some of these villages, they are built on flat alluvial river terraces. Maybe this is one of the causes because they amplify the ground motion. Maybe this is one of the causes why there was so much damage in these villages. But there is also, of course, some details and construction details that we have a look in details that have shown very poor performance in the construction. These are the main materials that characterize traditional buildings: stone that can be rounded or flat, or round earth in form of walls or blocks, and then these are traditional roofs. These are the type of buildings that we were seeing on site when we talk about from earth. So they are made of blocks, but very often these houses already have like very significant cracks along the different blocks. So you can see over there that there are these cracks that most probably they are not really caused from the earthquakes. So there are pre-existing damage due to the fact that there is a very lack of cohesion in the materials, most probably connected to the fact of a very poor compactation of the material itself when they were making the walls. But then there is not only that. I mean, the point is that many of these houses, they are originally in ram earth. They have like some stones. So generally the foundation is made of stones, but then Some parts of the walls have been replaced with stones, so there is this use of mixed materials, and make, of course, these houses very very poor. And then there is also, like lack of maintenance, but also because many of these houses, they are vacant or used for animals. And then there are the ones that are still around Earth and have been completely reconstructed internally. So from outside you cannot really see, but then when you visit the houses, you can see that they have added frames, columns, changing completely, which is the typology and the performance of these houses. Here we can see some of the typical failures that we can observe. I'm not saying anything new up to now. I mean, these are like, again, out of plane, so failures that you can see the separation between walls, or like very important corner failure, as you can see the one on the right. But what is interesting actually is to look at them more in details, and many of them actually they have these pegs that, as you can see, they are very ineffective. Pegs that are very smooth. There is a loss completely of the mortar, probably from the earthquake, probably not, we don't know exactly because it was very difficult to say by looking to these houses, but definitely they were like presence, so there was like a knowledge that probably has been lost over the years, over the time, because I mean, there is a presence of these elements, but are they effective? I mean, they have done, there is not a really pattern that you can say how these pegs have been inserted into the walls. Same things, I mean, also for stone masonry buildings, we have found in different cases these pegs that are inserted between the walls. And it's very interesting to see that these dowels in the corner, of course, they are done in order to prevent, so in some way they have prevented overturning on the walls. And here in this figure, like on the right, it's much more interesting because you can see that there is a crack, and that crack stops really where there is the pegs. But then probably there is no anything that is on the top. So there is, it looks like that the presence of these ties in some way control the crack propagation. With stone masonry, the major issues are the stones. The stones, because very often the way how they are built are multi-leaves, so they are like external leaves, and then they are filled with losing fill or maybe some mortar and smaller stones. The problem is that, I mean, we know that this leads to a leaf separation of the walls. So in the first case, we have just some disgregation of materials, but this type of leaf separation can cause even major failures. We can see here like different type of out of planes, like kind of earth failure when we have a significant loss of materials, also like corner failure. And now I'm just I want you to pay attention of these two different buildings. So we have stone masonry on one side and adobe. So this, if we look at the left side, so all the mechanisms that you see on the bottom are the ones that are can be identified on the buildings. I mean, it's very difficult to see that because the problem of these houses, that's probably the most complex things about looking into these typologies, is that it's very difficult to identify what is happening on the buildings because there are co-mechanisms happening at the same time. And indeed, I mean, I have highlighted in blue, actually, where we can see the corner failure. So there is a corner, there is also a wall on the other side that is failing. That loss of materials in yellow is representing like a shear failure. So on the top of the spandrel, on the pier over there. We have on the red, like this out of plane, and then there is also a bit of a pounding of the effect between the two buildings. So it's very complex, as you can see, to understand what's happening on the buildings. Same things also for the adobe, very similar here. We have different mechanisms that we can identify. The reason why there are co-mechanisms happening is because really there are so many different deficiencies on the building itself. And sometimes it's really, you need sometimes to try to understand what is happening. Again, so this is actually highlight the fact the patterns are very difficult to identify. I mean, we know at this point probably which are the main mechanisms that occur on masonry constructions, but in this type of building sometimes become much more complex identifications. From locally in Morocco, there is a lot of attention on trying to preserve traditional buildings, and these are some of the activities that are ongoing in Morocco. And like they do a lot of training. They try to involve from like little kids to explain how important it is to build like safer houses. And the point is that there is a little bit of misconception of what it is traditional houses in Morocco. And I'm gonna give you a couple of examples here. Here you see like a few examples over there of what they mean traditional. When they talk about traditional buildings, they are talking about houses built with traditional materials. But then these are combined with some modern materials that is the concrete. So you can see on the top like some roofs made on concrete, but unfortunately this is what we have seen as well. So completely we have completely loss of the roof, and here on the bottom as well you can see that beams are used as a lintels and also as a ring beam. But then again, these are the type of failures that we observe at this same type of what is traditional for them. So here there is like a lot of discussion on what we mean when we talk about preserving traditional houses, and which is the best way of preserving, which are the information that we're giving to locals, and whether they are correctly implemented. This is also another example, very similar to what I was, again, very often you see for them is when you talk about traditional housing, for them this is the new version of traditional house. So a frame in concrete filled with stones. And this is what is happening. You can see this many times, everywhere. That these type of houses, they have this type of failures. And this is very common because we know that the masonry work very well in compression, but these are type of system where all the loads are taken by the frames. So there is not that compression forces that may take the walls together. And so this is the type of failures that you see. You have this arch failure due to completely out of plane of the materials. Right, now I'm going to move to another typology that is the major typology, we have found mostly here. So confined masonry structures. There is a question here. Is this a very real confined masonry structure, or is it like a reinforced concrete frames? If you talk with the local people, they will say it's confined masonry. Sometimes it's true, so they are built properly, so in the sense they build to the walls first and then they do the casting. But in some other cases, it's very difficult to say whether these are proper confined masonry buildings. You can see failures where there is the walls detached completely from the columns. And even though, most of the confined masonry, as you can see from there, we have observed they perform quite well in terms of damage rate that you see over there, but I have reported here some of the most critical buildings that they fail for irregularity in mass, irregularity in vertical irregularity, and these are the type of failures that you can see that are due to weak connections. So you have a roof that has collapsed, or maybe actually the columns that probably have some hinges, and that's why then there is an out of plane of the walls and then the collapse of the roof. And here are some other samples. Very often these type of failures are connected to hinges in the columns, and this is a typical shear cracks that we have seen for many of those. Then we're talking about here. I remember that I mentioned about we have a big percentage of buildings have been classified as a mixed. Mixed, I don't know whether it's the correct terminology in this case, because mixed is very much for us connected to the definition of staged buildings. These are buildings that have been built in stage. What does it mean that? So you see many buildings that are incomplete. So they have walls, but they don't have roofs. So roof has not built yet, maybe. So they become, these walls, very highly vulnerable. And then you have mixed in the sense that you have houses that have a first level in stones, and then they added additional 1 or 2 floors as well, made of completely different materials, so concrete blocks with some frames. And then you have so many examples of this type of buildings that are very common. And again, you see a pattern in the sense, that you see so many buildings that they have these mixed technologies used at the same time. but it's so complex. First, to classify this building according to international building classification. Second, very difficult to understand the type of failures that is occurring, because every time the failures that we observe is connected to some deficiency of some specific material or some specific technology, so it's very difficult so definitely these are type of construction that needs further studies in trying to make homogenize also the existing classification. Then here we have some reinforced concrete buildings. Generally, we have a very few percentage of buildings that we have seen, but most of them they are constructed after the 2000. Damage grade, most of them DG1 or DG2. Then we have also a few that where we have seen that the damage grade is very high, and these are classic actually type of failures that you can see when you are on site. But what was interesting is that we travel a little bit further. So the star is actually where there was the earthquake. We traveled to Agadir, and Agadir there was an earthquake in 1960. The reason why we went there was because we were very informed that there was some damage, even the city was very far away. In Agadir there was these earthquakes, but you can see the type of buildings are completely different. Definitely they have been built following the standards that are exist locally. So definitely after the earthquakes, all these buildings have been completely rebuilt. Indeed, you can see some very little damage, some founding, but very minor, very minor. And this is actually a good news, let's say, in that sense. Right, so I'm going to talk about non-engineering construction. The first, we have look at some mosque. The reason why you see this, there are different villages. As you can see from these photos, these are villages that are severely damaged, but what you can see is always the mosque. It's always there. There is always a mosque standing, right? You know, these are different villages. The reason why mosques are there, they are still standing, is because they are typically community funded. So they are built generally with better materials, better technologies, skilled labor. So that's why you can see all these mosques standing on the completely destroyed villages. And we went to look at this mosque more, closely. You can see we went a little bit around. The major type of damage that we have seen are on the minaret. Very often we see pounding effect between the minaret and the prey areas, or some more structural damage on the minaret, but still are damage that can be, this mosque can be repaired. Then we also went to some schools. Schools perform quite well, I have to say, apart from very minor cases. And hospital, they were functional soon after the earthquake, so there was not any particular damage. So the health facility was not particularly affected. I'm going to move to the, this map that you see here came out very quick after the earthquake. So there was a lot in the news talking about that there was a lot of historical sites that were affected by the earthquakes. So they identified from the beginning that there were 27 historical sites affecting across different regions. We went to see some of them. The list is here. So we have built sites ranging from the 12th century up to the 19th centuries. But I have to say that it's very clear that there was many of them, the green one in particular, are international protection or under the UNESCO World Heritage. So there was a priority from the Moroccan government to consolidate the site for the tourism. And so only a few of them, but I have to say that generally they were well preserved, monuments, and then we have only a few of them that they collapsed. One of them, and this is one of the exceptions, is the Tilmel Mosque. The Tilmel Mosque, unfortunately, we didn't manage to get in. The picture that you see here is taken from far, so it's completely propped, but we heard that there was already under restoration at the time of the earthquakes, so maybe this is the reason why this mosque, and there was a collapse of the minaret, also the rear walls, so there was a lot of damage on this mosque. In general, as you can see from these pictures, we went at Benadou and Torrington Casbah, very well preserved. There are very little cracks that are around. This is a little bit overturning in the third pictures, or maybe some slight damage. But in general, very well preserved, in good state, maybe some spoiling. Can you see here, in these pictures, there is also the use of these pegs. They're actually built in the same way, very smooth pegs that are connected to walls. Of course, they had an important role in the walls because the walls has not collapsed, but you can see that the mortar has completely lost. Also, this is on the right, some ties, so that is also very common, visible in different walls, and to ties the walls itself. And then some stitches as well. So there was a lot of reparation that were done already when we went in the field. And then I just want to pay attention on this fort that we visited. This is not listed. It's actually in the middle of nowhere. There is not many documents talking about this fort, but we found very interested because this is an example of a fort that is built on a flat alluvial terraces that has very deep superficial deposit. We discussed this, Mike discussed this earlier, that most probably has amplified the effect of the earthquakes. But then, not only that, again, this is a really good example of the combination on how where they are built then is connected with some other heavy concrete slab were built on the top of this fort. So we are talking about an adobe constructions. Original floor was substituted with a heavy concrete slab, and we know, like in conservation in the 1960, 1980, that was very much common things to do when, there was the introduction of new materials for the concrete, so it was very much used. So you can see that actually this is a type of failure that you could observe very massively, this very thick slab on the top. I'm going this just to give a flavor of what is happening at the moment in Morocco. So as soon after there was an earthquake, so there was a lot of course, the kings announced to preserve the local heritage and their identity as a first things. So there was a lot of discussion, but at the same time, there were discussion also about restorations and stipends. So they mentioned, what was the amount that will go to people that need to rebuild or they need to restore the houses. But this was happening just at the beginning, and then from September to December, actually there was a assessment of the damage that has been done locally. Then in January, I would say 2024, they've started the some rebuilding the constructions. At the same time, some families start to get first installment for the reconstruction, and you can see how actually that progress. So we had in March that 86% people received their installments up to arrive to September, that most of the people start receiving also the second installments for the reconstruction. Recovery process is ongoing. We went back to Morocco in December 2024. It's nice to see actually what is ongoing. So there is a lot of reconstruction. There are many buildings that are rebuilt. They are rebuilding new houses. So you can see that from the beginning. There is a lot of work also in terms of reparation. That's also nice to see that. And then roads, that's been discussing a lot. So actually when we were in December there, it was, you can see the face from Mike. So it was very complicated because, the nice things that they were reconstructing on the roads, but the problem was that there was always very long queue to go and cross these roads. Yeah, that's all. I'm not going through the whole what we have in this, also because many things have been mentioned. But I would say, from the landslide point of view, Maxar and optical images were able to do some identification of the landslides, but in total 464. It seems that, this number is not a large number for an event like that. News were making us much more worried, but this doesn't mean that number landslide does not affect the communities. And then clearly all the geotechnical failure demonstrated that many of these failures are connected more to geological aspects more than topological. And then from a structure point of view, you have seen all the different type of buildings that we have assessed, the user remote sensing on improve our ability in try to understand the damage. But then we have seen all different typology. One of the major conclusion here is really how difficult it has been to try to understand the building typology and the failures connected to the different types, starting from traditional constructions and then looking to the mixed construction and also the confined masonry. Good things is that to see how the government has done a lot in order to preserve the monumental heritage. So they have received definitely a prompt attention. Reconstruction has started. And there are so many open questions still that needs to be investigated further. And this is the workshop that we're going to have on the 14th and 15th of May, so 10 days, no, 15, a couple of weeks. It's going to be an opportunity to discuss this further also with locals. And with this, I finish my presentation. Okay, this is very important. I just would like to thank all the supporter, our founder, and then all the other people that AECOM and other people that also have supported the mission. And then there are so many other, apart from the team, other contributors that has helped us during this journey that has not finished yet. Thank you.
Okay, so thanks a lot to our speakers for the very interesting presentation. I don't know if there are questions. We don't have much time, I think, but we have time for 2, 3, 4 questions. Vale, thank you. I don't know if it is on.
Thank you. One question for the buildings. It really caught my attention when you were showing the first buildings, like the more rural ones, how you mentioned they were really poor quality, and because of that, they have lots of failure modes. And I wonder, like, whether those buildings were actually well proportioned, and the fact that they have like many failure modes rather than one single one actually enabled them to resist lower earthquakes that are happening up to them, and therefore the traditional design was actually based on the fact that they don't have any ductility. Having many failure modes was actually beneficial to them. What is your opinion on that?
Right. We need to start from the point that many of these buildings, they had already many pre-existing damage. They are built with very poor materials. So we are talking about very vulnerable houses by itself already. So this is the reason why you see like so many mechanisms happening at the same time that are also very difficult to try to identify them. So what you see is really the impact of the earthquake on so vulnerable houses. So there is no beneficial in that terms. I mean, and clearly the only way to try to prevent this failure is that it should be done like a very effective preservation. That is what is the local government is trying to do, in try to rebuild better, let's say. And that's why there is a lot also training and trying to inform the locals on how to do better, because there is that identity in looking to traditional houses, but whatever you see there is so complex to the fact that we are talking about very disadvantaged area. So traditional house is seen still as the typology that is used by the poor people. That's the major issue there.
Thank you. Other questions? Yeah.
Thank you, Viviana, for wonderful, and Michael for a wonderful talk. I don't know if you looked into this because you were focused on the rural areas, but did you find out what the regulatory environment was around the schools and hospitals? So, you know, we know that they were more likely to be engineered. Was there any more scrutiny? Were they generally built by the government? Were they public buildings?
Yeah, they are public buildings, and I show some pictures. I mean, very few, just because the reason why was that we went there and there was not very, the damage was not significant. So most, I mean, schools were up like in function soon after. There were very few schools that they were damaged, and maybe are the ones in local villages that they were mostly damaged. Hospitals, we haven't actually seen any significant damage. It's true that we went after a few months after the earthquakes, but we were talking with the locals, and they were telling us that the problem was not really the educational or health systems, but it was more in the housing and these areas, disadvantaged areas.
Thank you. Other questions? Please.
Thank you. It's quite a good presentation, but one of the things that always puzzles me is once they have designed, it's gone through this damage issue, when they come to retrofit or rebuild, does the government support such that these structures will have the resilience for the future event should take place? What were the considerations that were gone into rebuilding these houses from an earthquake resistance point of view? Did they support in that concept in terms? I know they don't have standards, but what sort of contribution the government was trying to include?
Can I answer?
Yeah, sure.
Yeah. So what we learned during the mission is that in Morocco there are very limited expertise about earthquake engineering and focusing on structural earthquake engineering. We managed to have many contacts and collaborate with many people focusing on the geological part, but from the structural part, the expertise is still not well developed. This is one aspect. The other aspect is related to the fact that in many situations there is not the intervention of the engineer in the construction of the houses, especially in these remote areas. So for sure, to answer the question, so for sure there is a huge effort from the government, from the universities, from several organizations in order to promote a more resilient, more informed, and more safe and a safer design of structures. So definitely there is an effort in the direction, but to ensure that this is actually implemented widespread into the remote areas is not a very easy task. We collaborated also when we visited Morocco during a return mission. We were part of a presentation in a very remote area from, I don't remember exactly the name of the organization, maybe, a local organization that was trying to inform and teach, let's say, to local builders some basic requirements to improve the seismic design of these constructions. But so for sure it is a challenge. I have the impression, and I think that this is shared within the entire team, that there is a huge effort from Morocco to promote this innovative, resilient design, more resilient design, but definitely it's a challenging task. I hope I answered the question.
Yes, I think, but what I was trying to get is usually the universities and people, small organizations, do not kind of have the same influence to change that rebuild unless it came from the government itself. You see, so they gave the funding or to rebuild in whatever X amount. Wouldn't it be considered, whether you guys actually went and talked to the government organization to say, look, this is the whole country, you've lost 20,000 people, or what sort of numbers that's appropriate. When it comes from a government perspective, the take on the builders is much easier. Of course, there is always going to be a competency issue. You know, if they haven't got that expertise, it's very, very, very difficult, no? You see where I'm coming from?
Yeah. No, I fully understand the perspective. So in Morocco, the situation and the way it works is slightly different, and we have to learn also how to collaborate with local people. So the key university that we are collaborating with is UM6P, which is the university recently funded by the king, and is the one that has most connections with the government. So there is a significant influence from the university into what actually goes into the design code and the actual support from from the government to the population. Still, even if you manage to talk with the right people, are actions that are difficult to implement. So we are organizing a workshop on the 14-15
Yes.
of May, so in 2 weeks, organized in collaboration with the UM6P and with the participation of ministries and the government. So we are trying to inform the right people about the challenges and what are the required actions in order to make sure that whatever we learn during these missions is actually implemented in practice. But is not an easy task, especially because in remote areas the government doesn't have a full control, because houses are in many cases built, constructed, now repaired by local people, and so that's one of the key challenges. I hope, Other questions?
Sorry, Clive Shen from Arcings Realis. I think back to I think somebody raised that for the schools, hospitals, and malls, it doesn't really has any effect by the earthquake. Presumably those structures are not, because probably there's no seismic building design code. And I was wondering why these buildings sustain. It's just because they use better material, or they have actually adopt any codes to design the seismic?
Morocco actually has a pretty good.
Yes, the first version of the seismic code in Morocco was after the earthquake in Agadir in 1960, and then after that there has been a different version of the seismic code. So there is a seismic code, and definitely like health facilities, schools follow the design codes. Mosque is different. It's more related to better skilled labor that do the mosque, because they have more funds, because funds comes from the communities. So that's what that's why we observe. But of course there are some detailings. For instance, the pounding is really the classic type of failures or damage that comes from like probably a lack of knowledge from a seismic point of view. So but they perform quite well. But definitely it's because better materials, more skilled people. Traditional constructions, unlike villages, things become a little bit more complex. And then if you go to small cities, because all the confined masonry have been found in the small cities, but not all of them, they really have there is not very good quality controls on what is happening on the ground. That's also another issue. So there are design codes. The problem is that, as it happens very often in these countries when there is an earthquake or so much damage we observe, is because it's the quality control during the construction is poor.
Yes, so okay. Yeah, so they do have a design code, but
Yes.
just for the normal people, probably they don't have the budget, or the construction quality is really poor. Okay, thank you.
Thank you. I think we have time for one more question, if anyone. Otherwise, I think that we went well beyond the
Sorry.
required, the allowed time, so we can close the presentation here. I would like to thank again Mike and Viviana for the presentation, and all of you for attending the event. Yeah.